So you saw me on Monday as well. I'm still Chris, still one of Owner's students. I'll be giving the second lecture on interconnection networks. So this is just a continuation of what we talked about on Monday. We'll go a little more in depth on sort of the basics of how interconnect works. And then at the second half of this talk, I'll give you a few more sort of recent works. So some of Owner's work and some of my work actually, and then some of Kevin Cheng's work and other of Owner's students will talk as well about some of our actual research results on interconnects. So just to remind you, these are the readings. This is the same slide that I showed you on Monday. So we have a lot of papers. There are some of the basics that explain sort of how the virtual channel routers work that I explained on Monday. So the Dali paper, the Mullins paper, sort of this overview of the tile processor, which is one of the real processors that uses a mesh NOC. That's Wenslaff. Some of the more recent stuff. Patel was one of the first papers he described, one of the indirect switching networks between processors and memories, and then a few more, so a survey, and then the Bless paper there. Anyway, so I think one of those, so I think Bless is one of your required readings you had to submit a review for, but in any case, if you're interested in interconnects, and even if you're not, these are all good papers to read. So, but of course you're all interested in interconnects, so. Goes without saying. Okay, so interconnect. So I talked about sort of an introduction, overview of different terminology in interconnects and how they work at a high level. Last time I also talked about different topologies. So remember we talked about meshes, rings, hypercubes, various other topologies, and I talked a little bit about how buffering and flow control work. So I'll just sort of give a very high level overview, reminder of what we talked about. And then today we'll dive into a little bit more detail. So we'll talk about specifically how routing works, so a few different routing functions. Remember, routing is the problem of if I have two nodes in a network, A and B, and I have some number of paths and links between them, routing is which links do I take in order to get from A to B. So that can be an interesting problem if you have a network with a lot of different links, for example, a hypercube. I'll talk a little bit in more detail about router design and how routers actually work internally. We touched a little bit on that with a virtual channel router, but I'll say more here. And then I'll give a few brief just notes or high-level information on network performance metrics and some differences between on-chip interconnect, which is the more recent sort of NOCs that we've been talking about, and off-chip, which is the more traditional processor memory switch interconnect sort of thing. So after that sort of front matter, that's about the first half of the lecture. I'll try and give as much detail as I can on three recent bufferless deflection routing designs. Well, actually, bufferless and then minimally buffered is MinBD. So these are, so the first one is Owner's work, and the second two are some of my papers with my co-authors. And then I'll turn it over to Kevin for about the last half an hour for very recent work, HAT, Heterogeneous Adaptive Throttling, which is a sort of a way to get more performance out of an interconnect. So just to give a brief review, remember we talked about topology. So I'm showing three different examples of topologies here. The first one is a mesh, right? So I'm sorry, not a mesh, a crossbar, right? So we have, in this example, just 4 nodes. And I'm showing the sort of outputs of the nodes on the left and the inputs of the nodes on the bottom. And so remember, a crossbar gives every possible connection. So if any of these nodes wants to send traffic, send a flit or send a packet to another node, there's a crossing point or a switch element between any node. So if node 2 wants to send a packet to node 1, then this switch will be turned on after some arbitration. And the packet will just naturally flow from 2 to 1. So remember okay, so we talked about that. The next sort of class of networks that we talked about, and there are different ways to build these, are multi-stage logarithmic depth networks, right? So there are different ways to build this. For example, omega networks or delta networks or Banyan networks. But they're all sort of, at a high level, they all sort of look the same. They're basically composed of these switching elements in the middle of the network. And we have, again, the inputs on the left and the outputs on the right. And in between the inputs and the outputs, these switching elements sort of move the traffic around on different links so it eventually gets from a source to a destination. And the way that these switches connect gives various properties, for example, whether it's blocking or non-blocking, and different aspects such as path diversity. Okay, and then another sort of very common design, especially in more recent work, and one that we talked about last time, is the mesh. So remember, a mesh is basically just a 2D grid of nodes. And in this 2D grid, or actually n-dimensional in general, so you can imagine a 3D mesh if you have 3D stacking, for example. But in general, so at every point in this mesh, there's basically a processing element. So that's like a core, a piece of the cache, maybe a memory controller. And that connects to a router. And all of these routers connect together just to their neighbors, so north, east, southwest, for example. And when a packet moves, it just moves through the mesh along these links. And so the advantage of a mesh is that we get really good scalability because you only connect to your direct neighbors. You don't have global wires, for example, like you do in a crossbar. Okay. So remember I talked about the distinction between direct and indirect networks. The distinction is basically that in an indirect network, we have the nodes, which are sort of the endpoints, right? The elements that packets are addressed to, so processors, cores, cache slices. And so the nodes in an indirect network are separate from the switching elements, right? So in a crossbar, for example, we have 4 nodes here, and so they sort of have their sending half on the left and their receiving half on the bottom, if you will. And the switching elements, which are these junction points, are separate from the nodes. And then the same is true for the multi-stage logarithmic networks, where we have the nodes on the far left and far right, and the switches are these separate things that are in between the nodes. In contrast, a direct network like a mesh actually has a piece of the network, so one of the routers, associated with every node in the network. And in order for a packet or a flit to move from one node to another, it actually traverses other nodes or other elements in the network. Right? So in a direct network, basically, an endpoint is the same as any switching element or node in the network. Okay, remember we talked about blocking versus non-blocking. And the difference here is that in a non-blocking network, any connection can be made independent of any other. So in a crossbar, you can have essentially any permutation of the inputs on the left to the outputs on the bottom because we build every junction point to allow every possible connection. In contrast, in many multi-stage logarithmic networks, the network is actually blocking. Because if you set up a certain pattern of connections in those links in the middle of the network, it will actually block other connections from happening. Right? And so because of this property, you need some way for the network to actually either have some connections wait for other connections, right? So you could have, for example, some arbitration stage that says this link is already occupied, and so another connection can't be established until that link becomes free. Or you could have something like buffering in every stage of the tree or the network, where you actually sort of have traffic aggregate, and when there's contention, some of it waits in a buffer while the other traffic goes ahead. And so just a follow-up on, I think it was Birkin's question from Monday. So something like a mesh is blocking. It's considered blocking because of the contention, which can cause packets to require buffering. And as we talked about on Monday a little bit, you can do other things there too. You could deflect, for example, but it's still considered blocking in that case. Okay, and so just a few more things that we talked about. So we talked about cost. Remember, a crossbar is really expensive. So where n here is the number of nodes in the network. A crossbar is really expensive because for n nodes, we have every possible combination. So that's n choose 2, which is n plus 1 over 2, basically order n squared. Right, so actually it's exactly n squared junction nodes here. For a multi-stage logarithmic network, it's a little bit better. The height, if you will, or I guess the width is still order n because we have n nodes, and every node has some input at every level of the tree, but it's only logarithmic depth because we basically need one more level for every power of 2 increase in the number of nodes, and so it's overall n log n cost, which is obviously an asymptotic improvement over the crossbar. But it's still not ideal in terms of linear scaling. So a mesh is sort of the best we could hope for in terms of scaling because it's actually linear. What that means effectively is there's some constant cost per node that you add. Right? So if you make your chip 4 times as big, you only have 4 times as much cost for your interconnect rather than 4 times some logarithmic factor. Of course, the cost for that is that it's lower performance than, say, a crossbar would be. And then finally, we talked about latency. So remember, latency is just the amount of time it takes for traffic to go from some source to some destination. A crossbar is, again, sort of the best case here. It's the most performant option because you have a direct connection from every source to every destination. And so independent of whatever else is going on anywhere else in the network or in the crossbar, any source can send to a destination in constant time. You know, maybe it's a few cycles to arbitrate, one cycle to cross the fabric, one cycle to be received, you know, something like that. But it's a small number of constant cycles. Multi-stage logarithmic network, on the other hand, is no longer constant because this network grows in terms of depth when we add more nodes. But it's not as bad as something like you know, a mesh. It's only log depth because we have this sort of tree-like property. And so this is still fairly low latency, and it's fairly constant latency. Blocking can add some delay because you might wait for a connection to be established, you know, or you might wait in a queue somewhere, so there could be queuing delay on top of that. But the base latency is still pretty good. And then a mesh, you know, gets a little bit worse because we no longer have this sort of, you know, log tree structure. Now we actually have to, because it's a direct network, we have to traverse all of the nodes from source to destination. And so we actually have order square root n just simply because for n nodes, you know, it's square root n on a side if it's a 2D mesh, for example. 3D mesh, it would be cube root of n. But basically, the latency scales you know, now a little bit higher than either of the more costly options. Of course, the trade-off, again, is that it's linear scaling in terms of area and power. So that's you know, that's the trade-off you make. OK, any questions on this? Any things that are unclear? Great. So in the second half of Monday's lecture, we talked about flow control. Remember, flow control is basically the problem of if you have some resources in the network. So concretely, if you have things like links or buffer space, you need some way for packets in the network to not conflict, right? So if two packets both require the same link to reach the destination, one of them can get the link, but the other packet needs to do something else. So sort of you know, a standard option is to keep that packet in a buffer. And the way that you manage that buffer space is part of your flow control solution. So we talked about a few different options that have been proposed and used in the past. And the most basic buffer-based flow control is store and forward. So remember, store and forward basically says we have buffer space in the network. And whenever a packet needs to move from one node to another, first it reserves an entire packet's worth of space in its next hop. Once it has that space reserved, then it can move to the next hop along its path. And then once it moves there, it can likewise reserve space in the next node and move one more hop, so on and so forth. So basically, you know, this is simple because all you have to do is you have to reserve space and then move the entire packet and then do it again. The downside of this is that it's essentially a high serialization delay that's repeated with every hop, right? So if this packet is, say, 100 flits long, right, the extreme case, but let's say it's really long, we would actually have to wait for, you know, order 100 cycles for the entire packet to move and do that for every hop. So it's simple, but that adds a lot of latency. So sort of the general class of flow control that we talked about after that were cut through and then wormhole, which is an improvement on cut through. And the basic idea there is you want to pipeline things, right? So in store and forward, you have to wait for the entire packet to get to the next hop, right, before it can move to the next hop, and so on and so forth. If you do something like cut through, you can actually pipeline such that as soon as part of a packet is in one node, the head of that packet can keep moving to its next hop, right? So sort of in the you know, best case, the packet's basically spread over its entire path in the network, and movement happens sort of at a flit granularity. And so you reduce latency to basically just a single serialization latency plus a constant number of cycles per hop, independent of the packet length. And then, so the difference between cut through and wormhole, if you remember, is that is in the way that you handle buffer reservation. With cut through, you have to reserve an entire packet's worth of space in a buffer, so that if there's contention, the packet sort of you know, recollects itself in a single buffer. With wormhole, you can actually, or you do actually allocate space at the flit granularity. And so if there's contention, if there's blockage somewhere in the network, the packet can actually stop as it's spread over multiple nodes in the network. The advantage of wormhole is that you get better buffer utilization. So it's more efficient in that regard. So then the final thing that we talked about was head of line blocking, right? So with Wormhole, the problem is that if you have contention, and then the packet stops along its path in the network, it's actually occupying buffers along its entire path. And so we gave the example of like a turn lane in a left turn lane in the street is sort of the analogy where a packet may be waiting for some output link in a router and it's occupying buffers in that router, but it's actually blocking some other packet that could make forward progress if that packet weren't in the way. So here's the example we saw on Monday. Right, so the blue packet here is basically blocking this router in the top row because its buffer space here is full. But this red packet, which wants to go to this destination here, actually can't move forward because it's blocked by the blue packet. Right? And so the solution that we had was to use virtual channels. So we saw how that worked on Monday. Basic idea is you just split FIFOs into multiple lanes, if you will, and a packet only occupies one lane. And so in this case, the blue packet will occupy that virtual channel on top, but the red packet can still pass the blue packet and make it to its destination. OK, so that's just a brief review on flow control. Are there any questions about what we talked about? OK. I'm going to go pretty fast today to try and get through stuff, but if you guys have any concerns or anything, just let me know. OK, so the next thing we're going to talk about is routing. I mentioned on Monday the problem of routing in general is where you have a network with nodes, and if you have traffic from one node to another, say from node A to node B, routing is determining which links that traffic will take to get from A to B. Right? So if you have something like a mesh, you can imagine the routing function could get pretty interesting because there are a lot of different possibilities. Right? Let's say that we have this 4x2 mesh, and we have traffic being sent from node A to node B. Right? So there are actually, I guess, let's see. There are 4 different possible paths here, right? Because we could go all the way over and then down. We could go all the way over here and then down like this. We could do this. We could do this. And the choice that we make affects multiple things. It could affect performance because, say there's some contention in this router here, right? If our routing function chooses to go all the way to the right and then down, we may hit contention here and be blocked, right? Say there is some other packet coming through this way and it blocks all the buffers in this router. So it could affect performance. It could also affect latency. So in this lecture, I'm only going to talk about what are called minimal routing algorithms, which are, they take sort of minimal length paths, right? So here, any path that's minimal would be 4 hops. But there are algorithms, for example, that are called non-minimal algorithms, where you could actually go up and around and down. And you might want to do that if, say this entire region is congested. But if you do that, then you make a trade-off where you're actually adding hops to your path, and so you're actually increasing baseline latency, right? So you're trading off sort of uncongested baseline latency for potentially avoiding queuing delay in congested regions. So the routing function that you choose can affect performance, and it actually can also affect correctness, and we'll get into that a little bit, I think, in this lecture. So you can imagine there could be deadlock cases if you choose to route sort of in a bad way. I'll talk more about that in a little bit. OK, so there are a few different sort of broad strategies, if you will, to route in a network, right? And so the first one, and this is sort of the most commonly used and maybe the simplest to think about, is arithmetic routing. So the idea with arithmetic routing is that you basically want to define a function that, given a source and a destination and where you are currently, or maybe just where you are currently in a destination, it's some deterministic function that tells you where you need to go next, right? So a simple example that I could define on a mesh is actually one of the most commonly used. Is called XY routing. So the way that XY routing works, and actually the generalization to multiple dimensions is called dimension order routing, but in 2D it's XY or YX. The way that XY routing works is you basically say, I have in this mesh an X coordinate and a Y coordinate, right? And so what I'm going to do is, if I need to go from here to here, first I'm going to traverse in the X direction until I reach my X coordinate. And then once I'm in my X coordinate, so in other words, once I'm in the proper column for my destination, then I'm going to traverse in my Y direction to reach my Y coordinate. So in general, you can imagine if you have an n vector of coordinates, you basically reach your destination by reaching one coordinate dimension at a time. And so this is nice. It's easy to define. Basically, in hardware, all you need is a few comparators to look at your destination address and say, am I in the proper column? If not, figure out if I need to go left and right. If I am, figure out if I need to go up or down. So it's simple, and it turns out it's pretty easy to reason about too in terms of deadlock, which is a nice advantage. But so arithmetic routing works well when you have sort of these regular topologies where you can actually define sort of this logical function on how to get to your destination. Okay, but you can imagine that there are cases where that might not work so well. So for example, if I take this mesh, and let's say that there's some failure in the hardware. So let's say that this link goes away, right? Maybe it's a wire that gradually degrades in hardware or something. So this network is still fully connected, right? I can still get to any node from any other. Performance will be slightly degraded because my bisection bandwidth just got cut in half. But it's still fully connected. So we should be able to route from any A to any B. But if we try something like XY routing, obviously it's not going to work, because if I try and go from A to B, I go this way and I hit this broken link, and then what do? So you can imagine there could be ways where I could try and get around this by defining my arithmetic routing function in a smarter way, right? So I could say, go in the X direction until you hit a broken link, but then if you do hit a broken link, try and do something else. Maybe skirt the boundary of a broken region and then come around the other side. But that also gets sort of complicated to reason about, because then you have to think about the corner cases. What if what if it's not concave in that example, right? Or convex, I guess. So that gets messy. So actually, okay, I'm going out of order here. I'm going to talk about table lookup. But the generalization that you can make is if you can't define a nice, easy routing function that's based on a logic function like an arithmetic routing, you can actually do something called table lookup-based routing. So the basic idea with table lookup-based routing is you basically say, at every router for any given destination, I have a table that tells me which output to use for that destination. So you can think of this as more like in a conventional TCP/IP network. You have some number of network interfaces on a router, and you have some routing table that says this network goes here, this network goes here, right? The idea here is the same. You can imagine I would have, for example, a routing table at A that says maybe to go to this node, take this link, but for any other node, take this downward link because I want to eventually avoid this broken link, right? And then here, my routing table would say, okay, for anything in the right half of the network, you can't go right, you have to go down because this link is broken. So in general, you can basically construct these tables that say, for whatever destination, take this output. And you can imagine ways to build this efficiently in hardware. Maybe you have like a CAM that is prefix matching based. Maybe you have just all possible combinations table. But the basic idea is that you have a table, and so that way it's more flexible. That gives some other advantages as well. So if you use tables, you can do things like dynamic reconfiguration, where you could actually say, based on the congestion that I see in the network, every n cycles, I'm going to reconfigure my whole network and try and shift traffic away from congested regions, or rebalance routes or something like that. So that can be nice. Okay. And then there's the final scheme, which is called source-based. And so this is just sort of a middle point between the two. So arithmetic is based on I'm at a current location, and then I know where my destination is. And so I have a function of those two parameters, which tells me where to go, my output port. Source-based is basically saying, basically based on the source, so based on where I came from. So even if I'm in the middle of the network, I know that I came from A, and so I have some function that says when I come from A and I go to B, I want to go in this direction. So it's sort of just another way to specify the function. But sort of the two distinctions, or the two categories that I'll make a distinction between here are the function-based, so things that can be built in logic, and then the table-based, which are just a lookup table that tells you where to go. Okay, does that make sense to everyone? Good. Okay, I guess there are some pros and cons here too. Okay. Sorry, so actually, so source-based, so it's a little bit different. Okay, so the way the source-based actually works is when you send a packet into the network, you actually append some routing information. So it could be in the header, it could be in a footer, that says, this packet is going here, and here are the list of hops that it needs to take, right? And so for example, if you have 7 hops in the network max, you could have a 7-element field in your header that says, here are the next 7 routers to go to. And so basically at each router, you just look at the first destination, and you route to that next hop, and then you peel off that next hop. And so the next router will see the next hop, and so on and so forth. So sorry, actually, yeah, that's what it actually is. I misdescribed that. Anyway, so yeah, so that's source-based, and then there's table lookup. And so the advantage of source-based is that you can be flexible. At the source, you can pre-compute any arbitrary route, but it takes extra space in your packet. Table-based has the advantage that you have a small header, it's just the destination, but you need these lookup tables at every node. Okay, and then, yeah, more complex switches. Okay, so there are a few different types of routing algorithm as well, right? So, and this is sort of orthogonal to the way that you compute the route. So orthogonal to whether it's arithmetic, whether it's source-based, or whether it's table-based, the route that you take can have various properties. So the simplest is deterministic, which means for any given source-destination pair, so anytime I go from node A to node B, I always take the same route. So XY routing is an example of a deterministic routing algorithm because it's just a function of A and B, basically. This is nice, basically, because it's simple and because you don't have to worry about things like dynamic load balancing, right? So there's another sort of option here, which is that say that I have a network where some routes are or can be more loaded than others, right? So say that in this mesh, I sometimes get hotspots where maybe this is a memory controller here. So maybe this is, connects to DRAM, and a lot of traffic often comes here. So if I just have sort of a deterministic XY algorithm, or any deterministic algorithm, maybe there are some nodes that are talking to the memory controller, and they'll congest certain paths, right? So you want to do something that sort of spreads the load. So a nice way to do that is something called oblivious routing, where I don't take the same path every time. I try and spread my traffic over multiple paths, but I don't do it in a way that's, that requires tracking information about the network. I just do it in some random way, right? So I think that in a few slides I'll talk about valiant routing, which is actually an example of oblivious routing. The basic idea in something like valiant routing is you basically, from your starting point, pick a random middle point. So say I have a node here that wants to talk to this node here, and it's sending a fairly heavy flow, so a lot of packets. What it'll do if it's doing oblivious routing is it'll actually pick a random middle point. So say this node here, and it'll send the traffic there with some information on it that says, I'm just sending this to you to bounce it off of you, and the final destination is here, right? And so once the packet gets to this node here, it'll actually be resent, or sort of bounced, if you will, back to the final destination. And so the key insight with something like this is that if you pick this random middle point in a sort of a smart way, so say that, in general, if I have the whole network that's congested, if I pick the random middle point sort of randomly, but you can imagine you could do this in the nearby region or something like that, you actually spread the traffic around by using different paths. So that's one example of an oblivious routing algorithm. But in general, the idea is you try and spread traffic, but you do it in a way that doesn't require tracking network state. Okay, and then the final scheme is also trying to spread traffic, but so adaptive routing basically does this in a smart way. So there have been proposals over sort of the last N years where you basically look at the network and you somehow track congestion in the network, right? So let's say that we have this network and we have this hotspot still at this memory controller. We could have some, say, counters on all of these routers in the network. And these counters could somehow detect, OK, this path here is getting a lot more traffic than the other nearby routers. And so I know that this path is somehow congested. And so what I'm going to do is I'm going to somehow, say some traffic gets here, and I would have sent it on this congested path. Somehow I can dynamically choose to take a different path. And so the idea there is you basically give each router some notion of what the network state looks like. So either how congested its immediate links are to its neighbors, or how congested the regions are around it, or how congested the whole network is. And you let the router dynamically choose which route to take based on that information. So again, it's usually congestion-based information. It doesn't have to be. So you could be adaptive for faults, for example. Again, if you have that link in the middle missing, the router might adaptively detect that and take a different route, something like that. But that's the basic idea. Okay, so I mentioned a few different options. So how do you adapt? You could do it based on local feedback. Again, if you just know locally how many packets or flits have I sent over my immediate links to neighbors in the last n cycles, and then sort of use that as a proxy for how congested are the regions in that direction. You could have global feedback, so routers could coordinate with each other, right? Or could coordinate with a central sort of controller of some sort that says, okay, I'm going to aggregate statistics from the entire network and figure out this half is more congested than this half, so I'm going to try and shift traffic over the other way. Or you could have some combination of those. And then, so I mentioned just a few minutes ago, minimal versus non-minimal. Minimal means, again, that you basically can take any path as long as it's the same number of hops as the deterministic path. So basically, minimize the number of hops. So in a mesh, it's just the Manhattan distance. But non-minimal can actually buy you some performance in some cases, because even though you go a little bit longer statically, so your path is a little bit longer, you actually have less queuing delay because you're avoiding congested regions. Okay, so I guess I went through all of this already, so I'm going to skip over this. So just an example of XY routing. So the Cray T3D was, I believe, an alpha-based system, and basically the processors were connected in a torus, I think a 3D torus. And so it used dimension order routing. It may have been a 2D torus. I don't remember. Anyway, you can look that up. But the Cray used deterministic routing. Right, so it's simple. There's deadlock freedom, and if we have time, I'll talk about why. Downsides is that it could lead to high contention, again, because you could have these sort of static hot paths because of some flows having more traffic than other flows. And so it doesn't exploit path diversity, which could solve that problem. Okay, so I actually touched on this a little bit on Monday, but just to give a little bit more detail and to remind you. So deadlock happens when I have resources that have cyclic dependencies in general, right? And so in a NOC, deadlock can happen when I have traffic in buffers where all the buffers are full, and the traffic in each buffer requires some space in the next buffer in a cycle to make forward progress. So the simplest example, let's say I have these 4 routers that are sort of just adjacent neighbors here in a mesh, let's say. And I have packets in the input buffers in each router that want to go to the next router in a cycle. So it's a counterclockwise cycle in this case, right? And so if all the buffers are full, then none of the packets can allocate space at the next buffer in their path, and so none of the packets will move. But because none of the packets are moving, none of the space will ever free up, and so we have a deadlock, right? And so the way that we can handle this, so one way we can handle this is actually avoiding cycles in routing. And so I mentioned virtual channels as one solution. It's actually a sort of a more advanced solution, but you can actually solve this just by tweaking the routing function. And the way you do this is you actually change your routing function such that you restrict some turns. And by turns, I mean, let's say at a router you come in from the west and you go to the south. You restrict some turns such that there are no cycles in the possible paths you can take. And so I think we'll get another example of that in the next slide. And you actually, I believe, have a paper on this as well. I don't think it's required. Turn-based model, it's ISCA 92, glass and knee. But basically, so the idea there is you remove some turns from the possible paths so you never have a deadlock. Okay, and then I talked on Monday how you can also solve this problem with virtual channels. That's sort of a more performance solution, assuming you can afford the buffers. And the idea here is you just have sort of separate classes of virtual channels such that if you make certain transitions, for example, one common scheme is if you cross a certain horizon or date line in the network, you can transition from, say, pool 0 to pool 1, but not pool 1 to pool 0. So you remove cycles by restricting which virtual channels you can move between instead of which turns. And then the final option is just detecting deadlock. So just being optimistic, saying it probably won't happen or it won't happen that often. But if it does, I can detect it maybe by seeing, okay, packets haven't moved for so many cycles. Maybe there's a timeout, of some sort, or a watchdog. And then you can basically somehow break it, either by draining the network into some special side buffers or by preempting something so that you can get the network moving again. But just to go into a little more detail on the first option, which is turn-based. So this is the paper, a fairly fundamental idea, fairly basic idea, which is basically you look at, so you can consider the network as having what's called a channel dependence graph, and the Dally paper talks about this. The channel dependence graph is basically if every buffer in the network is a node in a graph, then you can draw an arc, a directed arc between nodes for any transition that can happen with a packet. So if a packet can move from one buffer to another directly, say over a channel, then you can draw an arc between those nodes. And if that directed graph has any cycles, then you get deadlock, potentially. And so the idea here is just to remove turns that you can make. So a turn connects one buffer to another, right, input buffers. Remove turns such that you don't have deadlock. OK. And so there are some examples here. You can sort of form these figure-8 type things where if you want to make a right turn, for example, maybe you have to go around and do a 3-stage left turn instead. But that actually removes the cycles in the network. So you can read the paper for more details there. OK, I guess I'm doing out of order issue here. But so valiance I already talked about. And it's an example of an oblivious algorithm, and the goal is to balance load. So basically, you randomly sort of distribute paths by choosing these random intermediate points. So it balances network load. Downside, of course, is that it's non-minimal, right? So you pick this random node that could be way out of your way. And so that adds to your baseline latency because it adds hops. So you could increase packet latency, in the worst case if that isn't traded off for lower network contention. So you could sort of get around that with a few optimizations. You could only turn it on at high load, for example. That's sort of the most basic thing. And you could also sort of be smarter about the intermediate node. So, so you could pick an intermediate node that's maybe fairly close to your destination in the same region, for example. OK, adaptive routing. So I mentioned there are sort of these two different classes of routing in general. And in adaptive routing specifically, minimal, non-minimal, based on whether you take the minimum number of hops or more than the minimum. And so, OK, I guess, yeah, I've sort of covered this too. Basically, you look at the network state and you say, I know where there's congestion, or I can guess where there's congestion, predict where there's congestion, and I'm going to route traffic in such a way that I avoid the congestion, if possible. OK, and then so it could be still productive ports. So productive means toward your destination, or it could be non-minimal. OK. OK, and then I mentioned this as well. So adaptive routing also helps you avoid faulty links, right? So that's sort of the basic idea is route around faults. And so this is a little bit strong. I think deterministic routing can handle faulty components if you design if you give the packet some state, right? So you could say that deterministically I can sort of follow the edge of a region that's been removed from my network. But it gets really tricky to think about, and it's really hard to prove that it works correctly. So basically, if you want to do something like this, you probably need to have something like routing tables, where you say, I know that this link is bad, so I'm going to change the routes for all the paths around that link such that I can sort of patch around it in the network. OK, so that was a super fast whirlwind tour of routing. Any confusions or questions, thoughts? All right, awesome. Let's talk about router design. So far I've given you the picture of a router basically as a black box. We went a little bit into it on Monday when we saw a virtual channel router with the buffers inside of it. But let's go a little bit deeper now. So let's look at a single router. So the first thing, there are different types of buffering in routers. So you'll hear about input buffered routers, output buffered routers. There are also routers with buffers in the middle. Basically, that means when a packet comes into a router, is it buffered first and then arbitrated toward its output? Or does it go through some sort of arbitration and crossbar first and then buffered at the router output? Or is it buffered at some intermediate point in the pipeline? Sort of the most common choice, and for a few reasons that I'll talk about, is input buffering, which means when a packet comes in to a router, first it's placed in a buffer, and then there's some routing and arbitration where eventually it'll leave the buffer and cross a crossbar inside the router. The reason you do input buffering is in order to give a better worst case, right? So in the worst case, only one flit can come into a router input per cycle, which means you really only need effectively 5 FIFOs with 1 write port per FIFO, if you think about the hardware implementation. But if you do something like output buffering, for example, in the worst case, all of the flits that come into a router in one cycle might head toward the same router output. So what that means is that if you don't have any capacity for buffering until the router output, you actually need to handle the case where all 5 flits, or say n flits for an n input router, can come in the same cycle. So right, we have n inputs. We actually need to handle the case where all of these go toward a single output. So we need redundant data paths to handle this. And then we need some large wide FIFO here that can actually write n flits into it in the same cycle. So we need a lot of write ports in the same FIFO, right? So that's the reason we do input buffering, because we basically have this guarantee that on a given input, we'll only get 1 flit per cycle. So essentially all recent router designs are designed this way. And so I mentioned virtual channels on Monday. You can design a virtual channel router where the virtual channels are actually separate FIFOs, which is sort of what this figure implies here. And in that case, you have something like a demultiplexer in front of the FIFOs and a multiplexer behind them. You could also design it such that this is like a single SRAM, and then you have virtual FIFOs within it, based on interleaving or address ranges or something. Not really fundamental, but basically you have these buffer structures that are independent at every input. Okay, and then once you buffer the traffic, eventually you'll decide, okay, this flit needs to go to this router output on toward its next hop. And so in order to affect that, in order to make that happen, you have basically something like a crossbar. So this could be just literally a full n by n crossbar. It could be some more efficient, sort of sparse data path like a log step network or something, indirect network. But basically you have some data path that connects the input buffers to all of the router outputs. So if traffic arrives from any input, it can get to any output. And then on the side of that, you have basically the control logic. And so what this does is it's a few different so there are a few different functions I'll talk about, routing, arbitration, all of that stuff. But the basic idea is when traffic comes in, you need to figure out where it needs to go first, so that's routing. And then you need to allocate the resources downstream to let it go there. So that's sort of arbitration and allocation. So I'll talk about each of these components. Any questions? Okay, so I'll talk about buffering first, then I'll talk about route computation. So basically, as I mentioned, flits come in, they get buffered first. And then once you get a flit, you do route computation, which is evaluation of your routing function to say where does this flit or this packet need to go next. Once you've done route computation, you need to basically arbitrate for the resources to let the packet get there. So that's, if you will, packet scheduling. Basically, if you have multiple packets that contend, the question is which packet goes first. And then once you decide that the flit or the packet can move on to the next hop, you have switching, so that's the crossbar. And then there are some other aspects as well you can think about. So for example, if you want to be energy efficient, you could do something like scaling link and router frequency. But that's sort of orthogonal to the rest of these. Well, I guess not quite. If you turn off a link, that matters. But so I won't talk about that too much though in this talk. Okay, so sort of a canonical buffered router, or virtual channel buffered router pipeline shown here. And so these are logical stages. In the next few slides, I'll talk about how they can be combined and made speculative to make the pipeline shorter. But this is what we'll start with. So there are sort of 5 logical steps, and this corresponds to what I just talked about on the previous slide. First, you have buffer write. So when traffic comes in, it's written to an input buffer. And then once you have the traffic, you do route computation. Once you know where it's going, you do virtual channel allocation. So what this means is that at a given router, you actually allocate space in the virtual channel in the packet's next hop. So this isn't allocating space in the virtual channel in this router. It's allocating space in the virtual channel in the next router. Sorry, actually allocating a virtual channel, not space in a virtual channel. Once you have that space downstream, you know that the packet can basically move on because you know that it has a place to go, basically. And then when it moves on, you'll tag it with a virtual channel identifier. So in the input buffer in the next router, it just goes straight into that virtual channel. So you can think of this as you're pipelining virtual channel allocation by one hop, where you actually allocate ahead. Okay, so once you have that, then you do switch allocation. So what that means is there could be contention for the crossbar input ports. For example, if you have multiple packets from a given input port and multiple virtual channels ready to go in the same cycle, and so you have to allocate for that, and also for the switch outputs. So I'll talk about how that works. And then once you have the data path allocated across the crossbar, then you actually traverse it. So concretely, that can happen in parallel with other things, but logically it's still a separate step. And then once you traverse a switch, then usually we consider link traversal. So that's the links between the routers as a separate pipeline stage, just because of latency reasons. It's hard to make that happen in the same clock cycle as the crossbar traversal. So logically, there are these 6 separate steps. 5 of them make up the router, and then 1 is the link between routers. But as we will soon see, you can actually combine some of these to make it shorter. Okay. So the first thing to realize is that if we have something like a wormhole router, remember in a wormhole router, once a packet starts to come in from one input and go to an output, it actually continues moving from that input to that output of the router until the entire packet goes through. And so this is what gives us the situation where you sort of have this packet spread out along its path in the network, because it maintains those connections along the entire path. This had the performance effects we talked about, where it can block other packets. But it also has this nice effect where in the router, we actually only need to route computation once for the head flit, or the first flit in the packet. And then once we do that, we can basically save the routing decision and keep this connection as sticky from input to output. So the route compute and the virtual channel allocation actually only need to happen once for a given packet, right? This doesn't help us with latency at all, because the body flits and the tail flit are going to come in after the head flit. So we can't hide this latency, or we can't shrink the total time. But this does help us in terms of energy, for example. And yeah, okay. Okay, so let's talk about sort of these tasks that the router needs to do at a abstract level now. So first, basically you can think of what happens when a flit comes in or when a packet comes in as decode. So we look at the routing information, figure out what type of packet it is, what needs to happen, and then routing. So we figure out, okay, this is its destination. It needs to go out the north output port, for example. Once we know where it needs to go, then there's basically this switch arbitration stage where we say, okay, it needs to allocate the data path through the router to get to the output. And then there's the actual data path, so actually traversing the switch. And so we can actually consider, in a virtual channel router a little more concretely, the switch arbitration becomes 2 separate steps. As I just mentioned, there's virtual channel allocation, and then there's switch arbitration. So you allocate the buffer space in the next hop first. Once you have that buffer space, then you arbitrate for the switch. But we can actually make a few of these things speculative, right? So we can actually assume that there will be space in the downstream router. So there will be a free virtual channel in the downstream router. And just go ahead and arbitrate for access to the switch to get downstream in parallel to allocating the virtual channel. So now that we've introduced speculation, speculation is a general concept. If you speculate and you're wrong, you need some way to recover, right? And so in this case, what recovery means is, we've allocated access to the switch. But if we don't actually have space in the virtual channel downstream, we just don't use the switch, right? So we'll just abort the switch traversal. So in this case, the cost of the speculation is potentially that we have more switch contention than we would have if we actually serialized VC and switch arbitration. But the benefit, which is in most cases much larger, is that you actually reduce the pipeline depth in the router. So you reduce the router latency by 1 cycle. So essentially, most or all modern virtual channel routers do something like this. Okay.
How do you roll back if there is no space?
So basically, the switch arbitration is just allocating access to the switch. But if you know that there won't be buffer space at the end of this cycle, you just don't send the flit across the crossbar. Yeah, so it's like an empty bubble, basically. Okay. So that was the first optimization. The second optimization, so we consider this buffer write as sort of a separate stage, right? Where something comes in, we stick it in the buffer first before we do anything else. And then once it's safe in the buffer, we start to think about it. We compute its route, we allocate space, we arbitrate space downstream for it, all of that stuff. But we can actually, this is sort of trivial, overlap route compute with a buffer write. So in parallel to writing the head flit into the buffer, we can go ahead and look at the head flit and start computing where it needs to go. Right, so we can do that in parallel as well. And then the next optimization we can do, okay, so this is the parallel virtual or VC allocation I just talked about. Right, so basically if it's not successful, you just need to try again in the next cycle. And so this gives us a pipeline that's only 3 stages long. And then the final optimization that we can do is that we can actually bypass the virtual channel allocation and route computation and directly arbitrate for the switch if there's nothing in the buffer. So this is called empty buffer bypassing. It gives us latency advantages. It also actually gives us energy advantages. It means we can completely turn off the buffer when load is low, and so that helps us out in terms of power consumption. But basically, we can do that as well. So I went really fast through that as well. Does anyone have any questions? Okay, so I'm gonna talk just a few more slides on sort of this high-level stuff on network performance metrics and on-chip, off-chip interconnect. Then I'll ask if there are any questions, and I can sort of give a review of any of the interconnect stuff. And then after that, I'll launch into the sort of recent research. So network performance. So sort of the canonical performance graph that you'll see in any on-chip network or any interconnect paper is this what's called a load delay curve. So the basic idea of such a plot is on the x-axis, you have the offer traffic. So this means the amount of data you're injecting into the network per unit time, per second, or per clock cycle. And on the y-axis is the latency. So this is the amount of time that a single flit or packet in the network takes to get from source to destination. And so the idea here is that if you have low offered traffic, you'll have essentially some baseline latency, right? And so this is basically just the latency it takes to get from one node to another in the network without any contention at all. But as you basically push more bits into the network, it creates more contention because packets bump into each other. Some packets need to wait for other packets in buffers. And so gradually your queuing delay takes over and you start to get more latency. And then in the limit, eventually you'll hit this point where basically the network saturates. And so this is where the latency curve shoots up. And that's where your offer traffic is approaching the actual network design capacity. So, in the best case, if you have a 1 flit width into the network at every router, that would be, 1 flit worth of bits per cycle per node. Usually it saturates below that because there are inefficiencies in the network, right? There are overheads with things like head flits. There's overhead with routing. There's overhead with, contention effects that make it non-perfect. But there should be some point where the network saturates. So let's look at this in a little more detail. So if you consider just the network at a very abstract level, you have nodes and you have wires between nodes. There's actually some minimal latency from any point to any other based just on the topology, right? So if we have this mesh here, and I want to get traffic from A to B, there's some latency that would be determined just by crossing this wire, this wire, this wire, and this wire, independent of the routers, right? And so that's sort of the best we could hope to do for unless we build some different topology, or unless we use different faster wires, or break the speed of light or something like that. Okay, but so the next step we can take is there's a little more reasonable or realistic bound, which is actually the minimum latency given by the routing algorithm, right? So here, when I talked about minimum latency given by the topology, this was sort of assuming shortest path from A to B. But if we do something like the Turnbased deadlock avoidance, or if we do something like adaptive routing, there's actually another minimum latency, which is I may not take the best path in terms of latency at any given point. So that's just another bound that could be different. And then the final bound is when we sort of consider the actual network design, right? So before I was just talking about topology. But now this is topology and routing and flow control, right? So now we're actually considering how the router pipeline works, how flow control works, and the time taken to, for example, allocate buffers, enter buffers, leave buffers, and go through the whole router pipeline. And so this is sometimes known as zero load latency, which basically just means if the network has zero load, so if there are no other packets in the network, how long on average does it take for one packet to reach from one node to another, right, for any two nodes in the network. And so this is sort of the realistic lower bound you can expect. And then as the load increases, you go up above zero load latency. Throughput, right? So before we talk about latency, now we're talking about throughput. Sort of the highest upper bound we could possibly hope for is the throughput given by the topology. So if you consider just the wires, the best you can hope for in terms of pushing bits through the network is keeping all of the wires busy in every cycle. Use all of the wires in every cycle. All right, you guys will hear me in stereo now. Use all of the wires in every cycle and basically keep them busy, right? And so, of course, that's not realistic because, again, we have these overheads in terms of going through the routers, and we have these overheads in terms of non-perfect routing and flow control and so on and so forth. So the next best thing we can hope for is the throughput given by the routing function. Again, the distinction there is just we may take different paths. And so that could be a little bit lower. And then the final, and this is the realistic actual upper bound, is the throughput given by the flow control. So once we consider things like buffer allocation and the way we arbitrate for contention, there's some realistic upper bound that we can achieve. And so typically you'll see in a buffered network, this saturation point is something like 0.6 or 0.7 flits per node per cycle, where one flit per node per cycle would be the optimum. So if you have, if you design your buffering strategy well, if you design your routing well, you can get fairly reasonable efficiency, but it's not going to be perfect efficiency because you have these overheads. Just to go into a little more depth, so what is the ideal latency? The ideal latency is basically solely wires, right? So basically we can consider the Manhattan distance. So if we're in a 2D mesh, Manhattan distance is just x distance and y distance between two nodes, and we take some propagation velocity. So this is some fraction of the speed of light in copper wires or something. And basically, if we take distance over velocity, we get time just to travel that distance. And then on top of that, we have what's called serialization latency, which is basically how long is the packet and how many bits per second can we push. And so there's some amount of time it takes just to get the last bit of the packet out the sender, and we add that on top of the propagation, right? So that's the best we could hope for. But if we look at the actual latency, of course, it's much higher. So we have the initial two terms, which are the optimal, just based on basically speed of light and the speed of our link. And then on top of that, we have the number of hops and then the time we spend in each router, plus the time due to contention, right? So you can consider all of the terms except for the last one. So this, so remember again, this is speed of light term, this is serialization delay, and this is time per hop. If we take just those three terms, that's a zero load latency. That's basically if nothing else ever contends, then all I have is time on the wires and time in the routers per router. But then finally, if we have contention, then basically sometimes one packet needs to wait in a buffer because some other packet is using the link that that packet wants to use. And so this is basically queuing delay, this TC. And so when you add all of those together, you get some realistic latency that the network actually offers. And that will increase with network load. OK, any questions on that? Good. So there are a few different concrete metrics you can care about. So packet latency is one. You can again, you can think about zero load latency. You can think about latency in a realistic system with a realistic load. Round trip latency is, in rough terms, basically two packet latencies. But this matters for things like coherence protocols, for example, where you request some data and then the data has to come back. So you care about the time for basically two packet transitions or two packet transactions. Saturation throughput is just basically the maximal throughput you can push through the network realistically. So that's basically the point where the load delay curve peaks. Or shoots to infinity. And then application level performance. And so this is sort of a high level. So far we've talked about interconnects as sort of these things that connect with these black box processing elements. But in the end, if you're designing the computer, you care about how fast the application runs, not how many packets you're pushing through the network. And so application performance is affected by network performance, potentially. If your system uses the on-chip network to connect to memory, for example, but it's not necessarily linearly correlated, for example. It could be some, maybe you need some amount of bandwidth, but then after a certain point, the network bandwidth doesn't matter, or something like that. And so it's also affected by things like interference, where one thread is close to another thread, and maybe in terms of processing elements, and maybe it causes packet interference or something like that. So we'll see more of that actually in the second half of today, which I'm about to get to. Okay, last thing I want to talk about. So far we've talked about interconnects sort of abstractly, in the sense of we have networks. We have routers. We have links between them. In modern or recent network designs, this has been on chip, right? So we have chip multiprocessors, and there's something like a mesh interconnect on the CMP. But conventionally, interconnects have actually been designed for off-chip designs. And so this is something like Janak Patel's paper in 1979 on through the 80s.